So we have started our discussion of ethers. Okay. We talked about nomenclature last time. With our ethers here, we have these common names as well as our IUPAC names. And common names for our straight chain alkyl groups were pretty straightforward. But we can also have these branched alkyl groups. And we want to remind ourselves how the heck we're supposed to name these things. So let's just do an example here. So we have these different common names for certain branched alkyl groups. The biggest category is, or kind of the most common one, are with these butyl common names. All right, so I'm just going to represent my parent chain here with the P. And if we have 1, 2, 3, 4 carbons all in a row, that is just a butyl group. But if I pick up one of those carbons and move it, we are going to have a different common name here. All right, so now instead of having them all in a row, I'm going to create a little fork at the end. Okay, any one of these common names that have this little fork at the end have this same prefix iso. And when we're talking about common names, one of the tricky things is it refers to the total number of carbons in the name. So my total number of carbons are 1, 2, 3, 4. So this is an isobutyl group. All right, if I pick up that carbon on the end and I move it to the second carbon, I'll leave the first one away from my parent chain. I guess my parent chain is connected to the second carbon. This is what we call a sec-butyl group. And there is a dash between the word sec and the word butyl. All right. And then lastly, if I take my parent chain and I make all 4 of those carbons into a giant T, a big old plus sign, this is a tert butyl group. And unfortunately, these are in pretty common use here. So we want to be able to spy these. Truthfully, there are a few more out there that I'm not so worried about you being able to spy, but the butyls in general you see referred to quite a lot. All right, so let's look carefully. Which one of these do we have in our ether up here? A sec-butyl group right over here. So this chunk is a sec-butyl group. Okay, the one on the other side, importantly, is not a butyl at all. There's more than 4 carbons. But again, I can spy that little fork on the end that's letting me know that this is going to be an iso. Everybody take a second. See if you can't give me the common name here. remember our common name is going to refer to the total number of carbons. So I know it's an iso because of that little fork, but it's got a total of 1, 2, 3, 4, 5, 6 carbons in there. Right? You don't do a parent chain business, it's total number of carbons. So this is an isohexyl group. And remember, to put our common name together, we got to arrange these in alphabetical order here. All right? But just to be a pain in the ass, when you do this arranging in alphabetical order business, you ignore the sec and the tert, the things with the dashes, and you don't ignore it if it's an iso. So alphabetically, what's going to come first here is that sec-butyl, because I'm going to ignore the sec part of it. And B comes before I. So this is sec-butyl, isohexyl ether. So we have these common names here for our butyl groups. A straight chain is a butyl group. If there's a fork, it's an isobutyl. If the parent chain's attached to the second carbon, it's a sec-butyl. And if it makes that little T, it's a tert-butyl. Okay? The other thing that we need to know is any of those branched alkyl groups that have that fork on the end, that 3-carbon fork on the end, get that iso prefix, followed by however many carbons there are. All right, so now let's look and do our IUPAC name. All right, remember for these branched groups here, we have their common name, which is what we just laid out. But we can also have their IUPAC name. For the straight chain, it's the exact same. It's just a butyl group. All right. For these other ones, though, we have to apply this systematic naming scheme. It turns out that some special ones have these special common names, but of course the IUPAC had to lay down rules for all possibilities here. All right, so what we're going to do is we got our parent chain, and now we're looking at this branched alkyl group here. All right, so now we're going to play the same game that we do before, where we're going to look and we're going to find, now this is like our grandparent chain here, and we got to look at our substituent and find the longest continuous set of carbons. That would be these 1, 2, 3, 4, or 1, 2, 3. When you number your parent chain, when you number the parent of the substituent, you always start with number 1 attached to that parent chain. All right, so my common name is isobutyl. My IUPAC name for this, with its methyl group on carbon 2, and it's 3 carbons long, this would be 2-methyl prop, but that's not propane because it's not a parent chain, so 2-methyl propyl. All right, see if you can't apply that same logic to our sec-butyl and our tert-butyl group. Alright, so again, we got to play that same game where we find our longest continuous set of carbons, but that carbon attached to that parent chain has to be carbon 1. So that means my longest set of carbons would be these 3 right here. I can't start up here because I can't have carbon 2 attached to my parent chain. Attached to the parent chain has to be carbon 1. Oops. Alright, so we got this methyl on carbon 1. So this would be 1-methyl propyl. Alright, and remember I'm putting it in parentheses here because really this would be part of a larger name. So for example, if I stuck that isobutyl group in the middle of this big long chain here, my parent chain are these 9 carbons, a nonane. Right, so for this molecule, you could have its common name. Of 5-isobutyl nonane. The 5, because I got to indicate the position of that. Or I could use that more systematic name for that isopropyl group, 2-methylpropyl. All right, and we put it in parentheses because it's got that 5 in front of it still. So 5, parentheses, 2-methylpropyl. Nonane. Okay, and just for the record, the tert-butyl group here, I have 2 methyl groups on carbon 1 in that branched alkyl group. So 1,1-dimethyl ethyl is my IUPAC name for a tert-butyl group. What's up?
Why do you have to put 1,1-dimethyl? Because wouldn't 2,2-dimethyl just end up being 2-methylpropyl, like isobutyl? Wouldn't it just turn into that? It would look the same.
Yeah, that's not a bad point, but I will say that is what they do. They do put both ones in the name. It's true. You couldn't have a 2,2-dimethyl ethyl. You would call it then, it would be your isopropyl group or your isobutyl group. But yes, they do put the ones in the name. All right, so now we're going to do the IUPAC name for this beast right here. Okay, the first step is we got to figure out which half is our parent chain. Right, if we chop at this oxygen here, which half is going to be the parent chain of this molecule, the left or the right? Right, okay, and I have to find my longest continuous set of carbons. 1, 2, 3, 4, 5. And now I have 2 substituents. One of them is just a normal old methyl group. All right, but now we got to name this big ugly thing over here, because this whole thing is a substituent. Now we have a branch in our substituent. So we got to play that same game. Where's carbon 1 in this branched group here? It's got to be the one that's attached to my parent chain. In this case, there's an oxygen in the way here, but that would still be carbon 1. Here's my methyl group. Take a second and see if you can't guess what this would be. The only thing I'm going to caution here is that what should this ending be on this group? I keep on wanting to call it a branched alkyl group, but it's not a branched alkyl group. It's a branched ether group, right? And what do our ether substituents end in? Oxy. Okay? So, I lied. For the sake of time, we're just going to go here. This would be 1-methyl, not propyl, but 1-methyl propoxy. All right, so now when I number my parent chain, okay, methyl with nothing after it would technically come first in alphabetical order here. So we have 4-methyl, 1-methyl propoxy, pentane. All right, so we're going to practice our branched alkyl groups here when it comes to naming our ethers. They're very common, especially because we have these common names for our ethers that are so widely in use. All right, and we talked about how we can make ethers last class by starting out with alcohols and putting it in that acid catalyzed environment. All right. We can also break ethers apart, what's called the dehydration. That's not. Hydration, my bad. Okay? And what we're going to be doing is breaking our ether apart. Okay, let's start out with a pretty simple ether here. Okay, this is also going to be an acid catalyzed reaction. So actually, let's take a step back. Let's remind ourselves what we mean by acidic conditions. And what we're going to do is we're going to react that ether with one of our hydrohalogen acids. Remember, very strong acids, HCl, HBr, HI, right? So we got this strong acid environment in here. And when we say acidic conditions, importantly, that means we cannot have any strong bases in our mechanism here. All right, let's think about what's the go-to strong base that you think about in your mind. Hydroxide, right? So let's just put that down. Hydroxide. Another ridiculously strong base would be if we had a deprotonated nitrogen. That's an even stronger base. Something that's just as good as hydroxide would be what's called an alkoxide ion, right? And what do all these strong bases have in common here? These negative charges, all right? So what we're going to see in our acidic conditions, no strong bases, so no negative charges, with three very important exceptions, and those are our halide ions, because although those have negative charges, they are trash bases, right? So no negative charges except chloride, bromide, or iodide. All right, but again, we're kind of trying to get good at drawing mechanisms here, and so we want to kind of spy when we take a wrong turn. If we do our mechanism and all of a sudden we make an oxygen with a negative charge under acidic conditions, it's like, oh crap, we got to do something else, right? And oftentimes what this is going to be, what you're going to be missing are these proton transfer steps. What we're going to see throughout the course of the semester as we keep on doing these mechanisms is we kind of manage our charges in our mechanisms by adding hydrogens or taking hydrogens away, okay? So acidic conditions, no strong bases, so not going to see any negative charges unless it's one of those halide ions. We also said that we are going to need something to play the role of an acid and something to play the role of a base in these mechanisms. For our acid, because it's acidic conditions, we can use that strong acid hydronium, or in this case, because that acid is specified, you could actually just use HBr as well. Either one would be fine, all right? And the reason why either one is fine is because if you buy a bottle of concentrated hydrobromic acid, it is not 100% HBr. It's probably about 60% HBr by mass. There is still a large amount of water in there. It's just impossible to get an acid solution and remove all of the water from it, right? So even when we buy the most concentrated solution of sulfuric acid, hydrochloric acid, whatever it is, there's always water molecules in there, which will always react to create hydronium. So either one of these are perfectly legal acids to use in your mechanism. Because I didn't just say H3O plus acid, I specified my acid. You can use HBr, but you could also use hydronium. But importantly, what base are we going to use here? We can't have that strong base hydroxide. We have to use that weak base water. All right, and what's going to happen is we're going to crack this ether in half here. On the one half, we're going to create an alcohol. And the other half is going to get that halogen. Which means that I'm going to backtrack because we didn't technically hydrate. We just decomposed. My bad. We had one hydrogen, but not a full water molecule. All right, so we're going to try to do our mechanism here for this reaction. All right. I'm going to take my ether, and like we said, we're not allowed to have any strong bases. The only negative charge thing we're allowed to have is that bromide ion. All right, and I'm going to make a mistake here, and I just want to make sure that we can see why this is a mistake. All right, I'm going to say, all right, this bromide ion is going to be a nucleophile. It's going to attack that carbon there, which is an electrophile because it's in that polar bond. And that's going to kick off that oxygen right there. And that will leave me with one of those products that I want. So that was a smart move. And then my other one is this thing here. And all I got to do is protonate that because we're in acidic conditions and I'm done. All right? Importantly, there was nothing illegal about my mechanism here in terms of my electron pushing arrows. They're all starting in a legal place, a pair of electrons. They're all ending at a legal place, an atom. But this is still the incorrect mechanism because we said we were under acidic conditions, right? So what's not allowed to be here that I put at this step? That alkoxide ion, all right? And again, we said that, okay, cool, that's not gonna work out. But again, we can sort of manage our charges by using these protonation steps. So I can't kick off that oxygen as is, or it's going to kick off as a negatively charged alkoxide ion. So what I can do first is to protonate that oxygen. And then when it leaves as a leaving group, it will leave as a neutral alcohol instead of an alkoxide ion. All right, so again, we're going to be playing with our mechanisms here. We just want to be able to spy if we make a mistake. Our nucleophile is going to attack that carbon, but that can't be the first step of our mechanism. We have to have a proton transfer step to that oxygen first. I don't care if you use HBr or H3O+, either one of those are fine. I will specify in your homework if you got to use one over the other, but the bottom line is we're going to protonate that oxygen first. And you'll just notice how that proton transfer step is going to help us manage our charges in our mechanism. Okay, so we got one more step here. I want everybody to take a second and see if they can't get me all the way to the finish line here, our alcohol and our alkyl halide. Alright, so now if my nucleophile attacks and kicks off that leaving group, now it won't be kicked off as that negatively charged alkoxide ion, but just a neutral alcohol, and I have my alkyl halide. Alright, so again, what we saw was that first step was a proton transfer. And that helped us manage our charges. Okay. So we're breaking apart our ether into an alcohol and an alkyl halide. And in this particular example, I started out with a symmetric ether. So there was only one possibility for what could be our products here. Only one possible 2-carbon alcohol and one possible 2-carbon alkyl halide. But what if I start out with an asymmetric ether? All right, if I treat this with my hydrohalogen, I got two possibilities, but depending on which half I'm going to make my alcohol. I can make that chunky tert-butyl half my alcohol, and then have a bromomethane, or I can put the bromine on the left half and have methanol. So which is it? All right, let's do our mechanism. And let's see if we can't learn from our mechanism which one of these two products would be more favorable here. All right, again, step one, just for the sake of doing it differently, I'll use HBr as our acid. Again, I gotta protonate that oxygen. All right, and that protonation step is there to help me manage my charges. Okay, so again, we had these two products here. Right, so how do I get to each of these? Well, let's take our bromide ion. Okay. I would get this top one here. Let me try to rearrange this a little bit better. Okay. How would I get to this top one here? Where would my halogen have to attack? Which carbon, which side, the left or the right? Right, right? So that would be, let me get my charge on there. That would be what I would get if my bromide ion attacked this carbon here. And how would I get to this product here? Which side would it have to attack? The other side. All right, so I want you to take a second and think, which one of these is going to be more likely here? The green path or the red path? Is my nucleophile going to attack that methyl carbon or that super crowded tertiary carbon? All right, which one is it going to have an easier time accessing? One of these is super duper sterically hindered. Whereas the other one is more accessible. So what do we think? Is bromine going to attack the more accessible one or the sterically hindered one? Yeah, it couldn't get to that sterically hindered carbon if it tried, right? It's like that would be the slowest reaction in the world. So we're going to take the green path here, okay? And so importantly, what we're going to note about these reactions and the particular product distribution that we get is because of our mechanism, right? Because of this mechanism here. Oh, I guess I didn't finish it, did I? We're going to have that halide on our, it's actually a halogen at this point. Our halogen on the more accessible carbon. What's up?
So would it still go to the other products as like a very minor product, or?
Yeah, but in this particular case, because it's a methyl and a tertiary, it would be like absurdly lopsided. If you had a secondary and a tertiary, yeah, you might see a little bit. It's really a kinetic argument how fast it's forming here, and you're just going to get one product that's just so much quicker formed. And more importantly, we're gonna be concerned with our major product. Cool. All right. We're going to now talk about synthesizing these asymmetric ethers here, and we're going to have a very similar logic that we're going to have to use. All right. These are what are called Williamson ether synthesis. If you want to make a symmetric ether, just add in some acid just like we saw last class. Boom. Super cheap, super easy to get yourself a symmetric ether. But how do you get an asymmetric ether? That's what we use this for, specifically for asymmetric ethers. All right? It's kind of the reverse of what we just saw. We're going to start with an alcohol. And the first thing we're going to do is treat it with a hydride, a metal hydride. This is if you take one of our group 1 metals and you combine it with hydrogen. Hydrogen is not considered a very electronegative element. It does not really take electrons, but that's because we're always comparing it to all the other nonmetals. Right? If we're comparing it to sodium, it's absurdly electronegative. So in this compound right here, really NaH, it's really a sodium cation and what's called a hydride, a hydrogen anion, where that hydrogen has stolen both of those electrons away from that metal because sodium's terrible at holding on to its electrons. All right? So what I always like to do here when I see these group 1 metals in arc ionic compounds here is I always erase it and put a negative charge on the other thing. All right? Because that sodium is not really doing anything other than giving up those electrons. We're going to be good and put that lone pair on there too because it's organic chemistry. All right? But importantly, the hydride ion here is what's going to be key to our chemical reaction. And then what we're going to do is add in an alkyl halide. All right, before we go on here, is this a reaction that is going to be occurring under acidic conditions? What do we see about that very first step here? Do we think that thing's going to survive under acidic conditions? No. And in fact, what we're going to see is this thing is going to play the role of a base. So these are basic condition mechanisms, which honestly are usually easier than acidic condition mechanisms. Under basic conditions, we just need to make sure we have no strong acids in our mechanisms. All right, so the first step here, sodium hydride. I mean, it must just be very, very good at its job. those hydrides are almost always used to deprotonate alcohols, to create hydroxide ions. That is like their claim to fame. In theory, you could use any strong base to do it. I don't know why, but they love using these hydrides specifically for that purpose, to steal a proton away from an alcohol. All right? And so that's exactly what we're going to see in this mechanism. Our hydride plays the role of a base, and it's going to snatch that proton away, creating that alkoxide ion. What other product, what inorganic product, so I don't even really care about it, but just let's make a point here. What inorganic product is created here? To be honest, that's probably why they use it so often. Hydrogen gas, right? I guess that's why they use it, is because then what goes flying out of your solution is H2, and you're not worried about the reverse reaction happening, because it's just going to bubble away. So now we're going to do our step 2, where we add in that alkyl halide. You know, halogens are kind of weird because they're good nucleophiles. They have a ton of electron density. But they're also kind of perfectly happy by themselves with that negative charge. They're also considered good leaving groups. So we see them playing the role of doing the attacking like we did in the previous step, but also being kicked off. And that's exactly what we have here. We have our oxide, our alkoxide ion, playing the role of a nucleophile and kicking off that leaving group. So everybody take a second, just draw me my product here, following our arrows. All right, so again, just keeping in mind our chapter here, we're talking about ethers. This was a Williamson ether synthesis, so we got an ether on the other side. All right, importantly, I've connected, and we can count carbons just to be sure, I've connected those 1, 2, 3, 4 carbons from my alcohol to those 2 carbons from my alkyl halide to create this asymmetric ether here. But looking at this ether, there was kind of 2 ways you could have done it. This one here, we're going to call method 1, where I made this half my alcohol, and this half was my alkyl halide. But now let's just reverse it. Now let's start with a 2 carbon, we're going to call it method 2. Now we're going to start with a 2 carbon alcohol. Treat that with that sodium hydride. And then we'll use that tert butyl bromide as our alkyl halide here. All right, I want you guys to try to fill in this mechanism on your own. I'm going to quietly kind of fill it in up here in case you get stuck, but just direct analogy to what we just did. How do I get from A to B on this? To be clear, my product would be that same product. All right, I'm just using a different half for the alcohol and a different half for the alkyl halide. Now my alkyl halide's the orange chunk and my alcohol's the green chunk. right, first step is to create that alkoxide ion to deprotonate that alcohol. That alkoxide ion is going to be a nucleophile, kick off that halogen, and that's going to leave me with that same ether here. So in theory, I could have done either method 1 or method 2 to create this ether, but I'm going to tell you, one of these is more preferable than the other. All right, and I want you to specifically look at that second step here. We're going to compare this versus this. Which one is more favorable? An alkoxide ion attacking a nice accessible carbon, or a very crowded, blocked up tertiary carbon? That first one, right? So with our Williamson ether synthesis, similar to before, we want our alkyl halide to be the half that contains the more accessible carbon. All right, to your point, maybe if you put these things together and waited 1,000,000 years, you would eventually get that same product. But if we're trying to make this particular ether, we're going to choose the quickest way, right? So definitely method 1 would be what we would call our preferable method. All right, where we're going to use that more accessible alkyl halide, and our alcohol can be as chunky as we want, because all we need to do is deprotonate it. Cool, and that's kind of it for reactions of ethers. We know how to make them and how to break them apart, and that's about all they do. All right, with the exception of those epoxides, those very special 3-membered ring ethers, and that's where we'll pick up with next time. They are much cooler than regular ethers. That is not how you spell preferable, huh? I am not a spelling major here.